السلام عليكم. This is lecture number 3. Today we'll discuss associated Legendre and spherical harmonics. In previous lectures, we did the separation of variables for the Laplacian equation of the potential phi. We found when there is m not equal to 0 that the associated Legendre differential equation d by dx of 1 minus x squared dp by dx plus L times L plus 1 minus m square over 1 minus x square p of x equals 0. I'm not gonna derive the solution of this equation. We know the solution is the associated Legendre function p sub L of m cosine theta. This is subscript and this is superscript. Cosine theta we call it x in the ordinary Legendre polynomial. Now the values of L runs from 0 up to infinity, and the values of m runs from minus L minus of L minus 1 up to 0 up to L. Now for positive m, if m is positive, we can write PLM of x in terms of this expression. M is the order of the associated Legendre function. So in this case, we derive the mth order from the ordinary Legendre function for positive m. For both positive and negative, we can use this expression to derive the mth order of PL of x. It can be shown that PL of x of minus m given by this expression, the orthogonality relation, orthonormalization condition is given by this expression integration from minus 1 to plus 1 dx, x is cosine theta, p L prime m, p L m of x, m is the same as this m for the mth order. This is given by 2 by 2L plus 1 L plus m factorial over L minus m factorial delta L prime delta L. This expression in the denominator gives the restrictions on m. Now, for the total solution, we have to multiply the theta part by the phi part. We already found that the phi part varies as x e to the power plus minus I m phi. This term is called the spherical harmonics y sub L m of theta and phi given by this expression. We already have the radial part for the Laplacian equation. Now let's talk first about this spherical harmonics. If m is negative, it can be shown that yl minus m theta phi is given by minus 1 to the power l to the power m y sub l m the star. This means complex conjugate of y sub l m. That's you have to invert this. That's replace I by minus I. The completeness relation, the orthonormality condition for this spherical harmonics is given by d phi sine theta d theta yl prime m prime star yl m of theta phi, where theta runs from 0 to pi and phi from 0 to 2 pi. This is equal delta L prime delta L delta M prime delta M prime, and the completeness relation is given by this expression. We need this expression for the future, in the future actually, when we talk about spectral representation of a Green's function. Now some examples of the spherical harmonics y0, 0, which is constant 1 over 4 pi. If you substitute here m0 and l equals 0, you get this expression. For L equal 1, M is equal 1, 0 or minus 1. Again, substituting in this expression, we get for y1, 1 this expression, y1, 0 is this, and 1 minus 1 is this. One important function of the spherical harmonics, M equals 0. If we substitute again here in this expression, we get for yl0 this expression square root 2l plus 1 over 4 by l by times pl. This is in terms of the ordinary Legendre polynomial. Now, any arbitrary function g of theta phi, where theta between 0 and pi and phi between 0 and 2 pi, can be expanded in terms of the spherical harmonics as in this expression. Now, to find this a sub lm, we have to multiply by d omega, which is sine theta d theta d phi of ylm star, the complex conjugate of ylm. And then doing so, and using the orthonormality conditions, finally we reach to a sub lm equal this expression. Now, for m equals 0, special case, al0 equal d omega g of theta y1 0 of theta phi, but y1 0 is given here in this expression. Now insert this, we have finally al02 over l plus 4 pi under square root times d omega g pl. Now the final solution for the Laplace equation is phi, which is function of r, theta and phi is given by this expression, summation over l from 0 to infinity, m from minus l to plus l of a sub lm r to the power l plus b sub lm r to the power l plus 1 times this spherical harmonics. This is the general solution of del square phi equal 0. Another important thing is called the addition theorem of spherical harmonics. We don't have time actually to derive this, but it's a very important theorem and we will use it later. If we have two vectors x and x prime, x has the parameters x, phi, and theta, x prime is radius and has angle phi prime and polar angle theta prime. Usually x represent a field point and x prime represent a source point. The angle between the two vectors gamma can be shown that BL of cosine gamma is given by this expression. Here YLM star theta prime phi prime, here YLM theta phi, and we know that cosine gamma is given by this expression. We also derived in a previous lecture this expression, 1 over x minus x prime represent a potential for a one electrostatic unit. Now in terms of this new expansion, we can write this potential, which is 1 over x minus x prime, as 4 pi times lm 1 over 2l plus 1 r smaller to the power l, r greater l to the power l plus 1 y lm star of theta prime phi prime y lm of theta phi. Again, we will use this in the next lectures, maybe, or in the future when we discuss Green's function again. Thank you.